All right, so let's talk about ED202 here, which is not worrying about the Metasploit shellcode, but it is the essence of the buffer overflow where you control the instruction pointer, and it does have a lot of other things in here like the 64-bit code and some online challenges. So here, let me shove these instructions to the side and bring back my Linux command line. Okay. So, clear. All right, the program is pwd.c. All right, and so I'll get rid of the colors. All right, so here's the main. It's going to call a program called test password and then print fail if that returns anything other than 0. The test password goes here. It asks you enter a password into a 10-character field, and then no matter what you do, it returns 1 and says you're wrong. There is no correct password at all. So this win routine, you should never execute it. This will always be 1. You'll always print fail. You will never have the else condition, which lets you win. And the point is, if you can gain control of the instruction pointer, you can redirect execution to this existing win code. So this is a simple attack. It does not let you inject any code and run the code you injected. It lets you reuse code that the developer put there. But this turns out to be extremely valuable because a bunch of defenses appeared around 2008 to stop these attacks where you run injected code, and this is called return-oriented programming. This is the technique to escape those defenses. So this simpler attack turned out to be more important as the defenses got stronger. So let me compile that one. I think I've already done it here, and so that should create pwd32, and there it is. So I can enter a password. All right. And let's fail. And by the way, notice I printed the address where the password is stored just so we can tell if address space layout randomization is on. And it's turned off. I turned it off earlier. This address is always the same. So it's not randomizing the address, which is what we want for these things. So, all right. Now we're going to debug it. db in quiet mode, pwd32, and we can do it without using assembly code here. We can work from the C code. So here is where it reads the password from the user, which can be up to 50 characters long, into a variable only has room for 10. So I want to break after that. So I can break at line 9, and now I can run the program. So if I run it and give it 3, 4, 5, 6, 7, 8 capital A's, and then do info registers, I see that the stack goes from 4FO to 508, and if I examine the stack, 4F0 to 508 is here. That's the stack frame. Here's the capital A's I put in, 41, 41, 41, 2 here and 2 there. That's the 8 capital A's. They fit in the room reserved for them, and it does not corrupt the return address, which is here, 5655, in the same segment as this area, 5655. So this is the program running as expected, and so if I continue, it will just proceed to the print fail, and I'm done. So now if I do a buffer overflow here, I'm going to run again, and now put in this password, which is A, B, C, D, E, F, just a lot of letters repeated 4 times. Now I do info registers, and I go from ESP to EBP, so it's 4F0 to 508. Now I examine the stack, and here it is. That's the stack frame to the word containing 508, and here you have 46, 46, 47, 47. Those are some of those letters. So if I continue, it's going to crash with that number in the EIP, and so it does, 46, 46, 47, 47. So now I can control this instruction pointer. And Now I need to choose a location to put in there, and for that I just want to run the win function. So I can disassemble win, and I can see that the function that's going to print the winning message starts right here. So that's the address I want to put in. So I'm going to copy that, and I'm going to have to make a Python file because not all those links may be printable. So I'll quit from here. All right, nano. Made a program here, and I've already got one, but I think I may need to change it. So this is the thing I just printed. Oh, good, it's right. Okay, good. So this is the address on my machine, and so I had to go, it was the 2 F's and the 2 G's of my exploit that ended up in the instruction pointer, so I need to end the code here, and here's what I put in after it, that address backwards, 17, 62, 55, 56, and then complete it. So when I print that, let's see if this works. ./exploit. There. And you see it does work, and it prints out strange characters here, one of them unprintable, and then carries on. So that should do it. And so if I run the program, which is pwd32, and let me get my instructions. I'm going to need to put it in a file. All right. So I'm going to need to run the program like I ran it there and put the output in a file, which I'm calling attack pwd32. All right, now I can run it in the debugger. And put a break at 9 again, which is going to show me the overflow, and I can run with --args from taking data from that attack file. There. That will run it feeding in that data that includes the address of the win function. And so now if I hit the breakpoint right after the overflow and look at the registers, ESP to EBP again goes from 4E0 to 4F8. So if I look at that, 4E0 to 4F8 takes me to here. So this is the return pointer, 56, 55, 62, 17, and you see that is in the right region. So if I continue, I now see you win. Then my program crashes with a segmentation fault because I did some collateral damage. I didn't fix the EBP, but I did manage to run the code which the developer did not expect me to run. So that's the main thing. Now the debugger is sometimes wrong. It's not a perfect simulation of the real code, so it's a good idea to just try it outside the debugger and make sure it works. And you do that with this. And you see it does print, you win, and then crashes. So my sloppy exploit does let me reuse some of the code, which is not what the developer expected me to run. And so if you look at the rest of this, then you can do this on a 64-bit program. You can just compile the same program on 64 bits and do it all again. Observe a crash. Now the registers have different names. It's RBP and RSP and RIP, and they're much longer, but the same principle applies. You overflow the stack, and then you'll find that these 2 bytes are the return pointer, all that. And so when you continue, it will crash. And now you can do the same thing, select a target address, which is much longer, and use the same kind of Python file, except you have to put in 8 bytes of code. Notice, by the way, it ends with a null byte, and I mentioned before, a null byte actually terminates the input. In this case, it'll work because I don't really need anything after this point, but it's a thing to be aware of. And so then that will run, and you again can get the you win message by redirecting code to the win message. And there are a bunch of one you can do on a remote server. I've set up a lot of these running on my server with GDB running, so you can do it all here. So here you can send a string to a server. So if you send it, say, AAA, and debug, it will run on the server. It's going to show you the source code, which I've redacted. There are some flags you can hit here. And you can actually, when I always do this, is I just control the URL up here. The string is right there in the URL. So you don't even need to use the form. So 4 A's go in there. Here's the code. It's then going to add a breakpoint, run taking the string you put in, show you where the win function is, and run info registers, showing you where the stack is, DC20 to DC48, and then dump the area. So DC20 to DC48 is here. That's the return pointer. And here's the 4 A's I put in, 1, 2, 3, 4. So you can develop it here. And you can do this even without having a machine set up. So there are some challenges here. Let me bring up a text editor. And let me show you how I like to do this. I just use a text editor. All right. So this didn't have the overflow yet. So the first thing is to fuzz it and form the overflow. So for that, you just need a longer string here. So let's put in a bunch more A's and see if that causes an overflow. All right. And so if you go down here, you see there's a lot more A's. Now the ESP and EBP end at DC48, which is here. So that is enough to form the overflow. It looks like about 7 A's back is where this started. So it's going to crash with 4141. So now I can control the instruction pointer. And now you can look and see what the requirements are. This one here, you just have to make the 30th character into a binary 7. And you'll get the first flag. And to get the second flag, you have to execute the win. Now, one thing you should know is if you want to send binary code in a URL, you do it this way. Let me get to my text editor. If I wanted to change some of these to 7, you put a %07 there. That'll be a 7 there. Let's try sending that up. All right. And so now if you look on the stack, I got 4141, and here's the 7s I put in, 7, 7, and some places here's the other 7s. So that's how you feed deck characters. So there's one flag you can get just by making the number 30 character a 7, and the other flag you get by executing the win function, redirecting code to it. And there's a series of other challenges involving the same thing. And like I say, you can do this even without having a Debian machine set up. You can exploit my remote servers through this form by just modifying the URL. So here's a 64-bit one you exploit on the server. And there's another one here where you get to exploit one with address space layout randomization, which is a little tricky. So you might want to try that. Even if you don't have a Linux machine, you can do the bottom half of this one.